My name is Bhanu Kumar. I'm in the School of Mathematics here at Georgia Tech. So I'm just going to be talking about using GPUs and the parameterization method to find and refine connections between tori and periodically perturbed planar circular restricted three-body problems. And you guys will understand what that means in a second. So, basic introduction. So when you have a spacecraft under the influence of one gravitational body, this motion is very well understood. Circles, ellipses, parabolas, hyperbolas, pretty simple. You throw in just a single other large body, so two large bodies in the spacecraft, and suddenly the spacecraft motion is totally unpredictable. It's quite chaotic in many cases. It's very sensitive to initial conditions. So now what's a good program to understand this? Basically, it's to find invariant objects which organize the spacecraft dynamics. Such objects include equilibrium points, which hopefully everyone has seen at least in an undergrad differential equations course. But there's also periodic orbits. Basically, if you started someplace, then after some time, you'll come back to that same spot. That's a periodic orbit. And then there's invariant tori, also known as quasi-periodic orbits, in which essentially your motion is not governed by one frequency as it is in a periodic orbit, but by two frequencies. And you might not come back exactly where you started, but you'll stay on essentially the same torus, where a two-dimensional torus is shown in the picture. You can see the trajectory stays on that torus. And then there's also stable and unstable manifolds, which I'll talk about in a second. Basically, what an invariant set is, if you start on this, that you'll stay on it. That's what an invariant set is. So now we have equilibria, periodic orbits, and invariant tori. These are examples of bounded motion on bounded invariant objects, and stable and unstable manifolds are just unbounded, but completely natural, just under gravity pathways to and from these bounded invariant objects. And if you have a stable and an unstable manifold intersect, this gives you a natural trajectory that goes from one object to another object. So we're interested in finding these. And just everyone's favorite face portrait from undergrad diff EQ, you can see the two red lines here of the saddle point are the stable and unstable manifolds of that equilibrium point at the origin. And here's an example of an intersection of stable and unstable manifolds going from one equilibrium point to another one in a nonlinear system, also called a heteroclinic connection. So now the model, basic model a lot of people use is a planar circular restricted three-body problem. In this, you have two large masses, M1 and M2. They go in a circle around each other, and then you have a spacecraft moving under their gravitational influence. Normally, we use rotating coordinates so that M1 and M2 are always on the x-axis. And the equations of motion here are Hamiltonian. X, y, and their momenta, px, py, follow the typical Hamilton's equations of motion. And the Hamiltonian h sub o for this is given below. It doesn't depend on time. And this is a picture of what it looks like. You can see M1 and M2 lie on the x-axis, and the spacecraft, you just see under its influence. And you normalize units so that mu is the mass ratio, M2 divided by total mass. So now, if you throw in a periodic perturbation of this, essentially a periodic forcing, then there's lots of such examples, like a four-body model where you have another large body, or a planar elliptic problem where you assume that M1 and M2 go around each other in an ellipse. And in this case, essentially, instead of just having x momentum, y momentum, px and py, you also have a perturbation phase angle, theta p, and the equations of motion are still Hamiltonian, but they depend now also on an additional angle. So our extended phase space is 5-dimensional, and the strength of the perturbation is given by epsilon. Now, in the planar circular problem, without the forcing, you have lots of unstable periodic orbits, and we can show that these persist as unstable 2D tori in periodically perturbed, periodically forced planar circular models. But since the phase space is higher dimensional, the state space, you guys might know this as, the methods from the planar circular problem don't work for finding intersections of manifolds and connections between tori. So we need new methods, and that's what this talk is about. So first thing, we are able to reduce the dimension of our state space by taking what we call a stroboscopic map. Basically, all this is, you take any point in your extended state space, the 5D state space, and propagate it forward by the equations of motion by time 2 pi divided by the bit perturbation frequency. And because of this time, in that much time, the perturbation phase, theta p, goes around by 2 pi, so it's essentially fixed under the effect of this map F. So by doing this, we can reduce the dimension of our phase space from 5 to 4, and also the tori, which originally had 2 frequencies, one of those can be disregarded. So the tori go from 2D to 1D, and it's much easier to deal with these. And these tori can be parameterized using a function of one angle, k of theta. And now each 1D torus of this map F has 2D stable and unstable manifolds, which you can parameterize using one angle. T just represents the set of angles, and then one real number. And it's a function W of theta and S, which is given as shown. It's a Fourier-Taylor series, so a polynomial in S with theta periodic coefficients W sub k. So now these parameterizations are only valid for certain S values, say negative D to D, and we can use the following formulas to find parameterizations outside of that range negative, the manifold points outside that range negative D to D, since F is just a numerical integration. Lambda is either greater than 1 or less than 1, so you can take k big enough to make this happen. So now basically we want to take these manifolds we have and intersect them by, first we restrict the search for connections, then we discretize these as meshes, and then finally refine them. So first step to kind of restrict our connection search, we define these subsets of the manifolds. You don't need to concentrate too much on the above formulas. Just main thing is that applying F to any of these sets U sub n, these are subsets of the unstable manifold. If you apply F k times, that gives you U sub n plus k, and applying F k times to S sub n gives you S sub n minus k. So essentially, if you have some U sub m intersecting some S sub n, you can show that applying F an appropriate number of times, you end up with another point on the same trajectory in a pair of layers, say a form U sub n and S sub n, or U sub n and S sub n minus 1. So basically, instead of having to search, say, whether U sub 5 intersects S sub 2, you just need to check if U sub 5 intersects S sub 5 or U sub 5 intersects S sub 4. So that restricts our search. After that, to discretize the manifolds themselves, we essentially form meshes. So let's say we have the parameterization. We compute W of theta and S at a grid of theta and S values, say theta sub I and S sub k, for some discrete equally spaced grid of thetas and possibly unequally spaced grid of S. Then you connect consecutive theta and consecutive S values to form a grid representation of the manifold, a quadrilateral mesh, and then you can connect diagonals to form a triangular mesh. So now, and this is what one of these meshes looks like. So now let's say you have 2 manifolds which are trying to intersect like meshes. We need to check if the appropriate layers, the U sub n's and S sub n's, intersect each other. These are just going to be subsets of the full manifold meshes. So let's say you have WU1 and a WS2, unstable and stable manifolds, pathways to and from 2 different objects. Let's say I and K represent the points on the unstable mesh, and J and L represents the points on the stable mesh, the indices. So now, first step, we define lots of triangles and quadrilaterals. Just these are the vertices on each of them. And we need to check if any quadrilateral on one mesh, on the unstable mesh, intersects any quadrilateral on the stable mesh. And remember, this is all in 4D space, so it's a little more complicated. This is just a graphical representation of what this looks like. You can see each QU is made up of a TU1 and a TU2, where the vertices of these triangles and quadrilaterals are given here. Normally, however, if you want to track every quadrilateral on even on one layer mesh against every quadrilateral on the stable layer mesh, this results in billions of possible checks. So we want to first run everything through a cheap rejection test before applying the expensive precise test to only non-rejected pairs. So the first step is this bounding box test. It's a very simple concept. So for example, this is we just illustrate this in 2D, but it works the same in 4D. You can see the quadrilaterals on the left don't intersect because the minimum y-coordinate of the leftmost quadrilateral is larger than the maximum y-coordinate of the other quadrilateral of that pair. So you know they can't intersect. And you can do the same with x, px, and py coordinates, all 4 dimensions. So if a quadrilateral is not rejected by that, then proceed to the Molar test, which is due to a computer graphics person given in the below citation. And we run this if the bounding box didn't reject it already. And we basically check whether all the 4 vertices of one quadrilateral are on the same side of the planes formed by the other quadrilaterals constituent triangles. And of course, if all four vertices of a quadrilateral on the same side of the plane of another triangle, you know that the triangle and the quadrilateral can't intersect. And this is pretty simple. Essentially, all we're doing, we find the equation of the plane using old methods from your old pre-calculus class in high school, cross product to find the normal of the plane formed by the triangle, and then use that to get the equation of the plane, plug in all four vertices of the quadrilateral, and see if the resulting values are all the same sign. If so, you know that the quadrilateral is contained on the same side of that plane. Finally, the ones that are not rejected by this Molar test or by bounding box, you need to check whether they do in fact intersect. Now this is just a system of linear equations given in the middle of the slide. These quadrilaterals, of course, are made of triangles, so now we just test triangles against each other. And if A, B, C, and D from this equation that you solve, it's a 4x4 linear system, not conceptually too hard to solve, although computationally you want to avoid, which is why we did the other tests. If A, B, C, D satisfy certain inequalities, we know the triangles intersect in 4 dimensions, and then you can approximate solutions to an equation which we need to find later. Now, we implemented this algorithm in Julia using OpenCL. The rejection tests were on the GPU, the precise tests on the CPU, and we assigned each GPU thread a different pair of quadrilaterals to check and tested this all in the Jupiter-Europa planar elliptic restricted three-body problem. This is a relaxation of the circular problem where you assume M1 and M2 can go in an ellipse around each other. And basically, we found several orders of magnitude improvement in bounding box runtimes, doing that on the CPU, on the GPU instead of the CPU. And then the full intersection search, doing it on the GPU, runs very fast, both on a laptop and really, really fast on a high-performance computing platform. And this is just an example of several of these intersections found from the manifold mesh intersection search and in the example we used. Finally, once we have approximate connections from the mesh search, this is the equation that we're trying to solve here for theta u, s u, theta s, and s of s. We want to get more precise solutions because the meshes are essentially linear interpolations of the manifolds. So now we want to do differential correction, essentially a damp Newton method. So we need the partials. This can just, those parameterizations I showed you earlier. We had this equation that's at the top of the slide. You can differentiate it with respect to theta and s, and you just choose k big enough so that lambda sub u to the negative k times s is within the fundamental domain of the parameterization, which, as I mentioned, is where the Fourier-Taylor series is valid. Once you choose k big enough, then the rightmost partials, you can evaluate those just using differentiation of trig functions or differentiation of polynomials. That's your old Calc 1 class. And then this df to the k is also a known problem. It's called it's a state transition matrix for those of you who might be familiar with that. So you could use this with a damp Newton method to correct solutions that we found for the mesh search of the equation we were solving here. And we were able to do it to high accuracy. And here's an example of the differential correction. So essentially, using all of this, we can find heteroclinic connections, intersections of manifolds, pathways to and from certain invariant tori in this higher dimensional 5D phase space, 4D phase space of the maps. And we defined the concept of layers to restrict our search, discretized the manifolds as meshes to allow us to use GPUs to search for intersections of meshes, and then finally did differential correction using the parameterizations. So, of course, there's some future applications to other systems as well. So I guess if there's any questions, I'd be happy to take them at this time. Thanks for listening.